The way this setup works is twofold. One is the excitation part of geometry and the other is the collection part of geometry. In the excitation part, a white light source, in this case a halogen lamp, is directed through a series of lenses and a dark field condenser, which makes a cone of light that then illuminates the sample. The cone of light illuminates the sample, and because of this there is a scattering of light by the structure present on the sample surface. The collection side of the setup has an 60x air immersion objective with a numerical aperture of 0.65. What this does is, by choosing this appropriate numerical aperture of the objective to be less than that of the condenser, we are only collecting the scattered light. Then this image is translated either to a visible camera, which is there on the left hand side port, or to the spectrometer, which is on the right hand side port. Once the light is transmitted through the lens system to either of these parts, we can take an image or measure the spectrum of the single particles that we are interested in. We are currently studying the angular dispersion of surface plasmons, which can be excited on thin films. This kind of arrangement or excitation geometry is called a Kretschmann configuration. This again has two different parts, the excitation and the collection part. In the excitation part, a white light source is used, which is coupled via a fiber, which is then passed through a polarizer, so that we can control the polarization of the light that is incident on the prism. Then the light hits the prism, and on the other side of it we have the sample. The reflected light is then collected through a set of objectives and analyzed using a small spectrometer. In this case, a portable spectrometer is used, which allows the system to be movable. In this setup, we use a set of converging lenses for illuminating the sample and collecting the transmitted light, which is then analyzed using a spectrometer. We can measure the transmission spectra for different values of strain applied to the sample and understand the correlation between mechanical deformation and optical response.